Now, so far the spectra we've looked at have all been pretty straightforward because we've always been able to see the parent peak. But in some cases, and this is perhaps more common than we might think, if we have a particularly stable carbocation that can form, the parent peak isn't always visible. So if we look at the following compounds, we have pentane, and we have 2,2-dimethylpropane, which has a common name of neopentane. Both of these have the same chemical formula, C5H12, which means they would have an M+ peak of 72. But their spectra are very, very different. And so let's look at their spectra and see if we can figure out which one is which and figure out why they're so different. So here's one of the two compounds. And I think what's particularly noteworthy that we should see over here is, what do we find at 72? The answer is we find nothing. We do have a very prominent peak at 57, which is 15 less. So we know we have loss of the methyl group. Our other spectrum, though, while it's not the largest peak in the spectrum, does have a peak at 72, which is our M+ peak. It also has an M-15, as well as an M-29, and plenty of other peaks. So which one is which? Well, let's think about what happens in each of these when we lose a methyl group. What does the resulting carbocation look like? Well, for pentane, it's this. But in the case of neopentane, it's this highly stable tertiary carbocation. Well, it turns out in many cases, when you get a very, very stable carbocation, that will result in sometimes the parent peak not being visible at all. And that's what's going on here. So this first spectrum, the one that had no parent peak present, that's the 2,2-dimethylpentane or 2,2-dimethylpropane, or neopentane. The parent peak is basically not visible because it has such a stable fragment that can form. Whereas pentane is not nearly as, doesn't have that any sort of tertiary carbocation that can form, and so we are still able to see the parent peak. Now, this can also be true for compounds that fragment easily. So we're now going to look at the spectrum for one octanol, C8H18O. The M+ here is equal to 130. What happens on the actual spectrum? Well, you can see the spectrum actually stops at 115. If it kept going out here at 130, we would see nothing. Why is that? Well, alcohols fragment very easily. But they fragment in a very specific way. So if we know that a compound has an alcohol in it, and that's something we can figure out pretty easily, right? We can figure that out from the IR spectrum. But if alcohol, and so what happens is for mass spec, alcohols will dehydrate, which means they lose an OH and an H. And so for most alcohols, the highest peak we see is mass minus 18. So for this molecule, which has a mass of 130, mass minus 18, or we sometimes will call this one mass minus water because that's what's being lost, is 112. And that is consistent with the highest peak we see here. Again, common property for alcohols.